So the last part of relativity is really the most interesting. Well, maybe not. I think time dilation and length contraction are pretty interesting amongst themselves, and the fact that we can actually time travel, that we can travel in time, forward in time at a different rate than somebody else is pretty interesting. And the fact that relativity also predicts, and we didn't have time to show this, but that you can't travel back in time. It does predict that we can't travel back in time, so we really don't think that that's something that will ever happen. But some really other very interesting things that connect to different parts of science are the dynamic quantities in special relativity. Now remember, the dynamic quantities in physics were things like momentum, mass, energy, or K, kinetic energy, E, total mechanical energy, and things like that. Okay, so so we have so far done the kinematic quantities, right? The distance, velocity, acceleration, and time, and now we're doing the dynamic quantities, the forces and energies. Okay, so let's start with momentum. We're not going to do many derivations here. We were just going to do more of an overview than anything. Let's start with momentum, and let's just think about if you have a mass m1 going at a velocity u1, and it hits and sticks to a mass m2, which is going at velocity u2, and they stick to each other, right? And so you've got a final velocity u final, and that's going to be m1 plus m2. You can conserve the momentum by doing m1 u1 plus m2 u2 equals m1 plus m2 times u final. This is actually a vector equation, but since I'm doing one dimension and everything traveling the same direction, it doesn't matter. Let's give some numbers here. Let's make m1 equal to 500 kilograms, m2 equals 1,000 kilograms. Let's make u1 equal to 3 meters per second, and u2 equals 0. So the second object is not moving relative to the road, if we're talking about cars and trucks on the road going at low speeds. And if we then conserve momentum, what you're going to do is you're going to find that u final is equal to, go ahead and do it yourself, but you're going to find that u final equals 1 meter per second in the plus x direction if we really use vectors, but I'm just being quick here. Okay. Let's now do something fun, like transform this momentum conservation to the frame of reference in which it's in the u final frame of reference. So we will say that we're transforming to a frame of reference where v is equal to u final. Or really, we're just transforming to a frame of reference O prime that is moving at plus 1 meter per second. Okay, so we're going to do a Lorentz transformation to that frame of reference. Now, before I go on, remember, postulate 1 says that all of our physical laws, if they work in one frame, one inertial frame should work in another inertial frame. So what does that mean? We've already done this kind of problem many times. What it means is if momentum is conserved in frame O, is momentum conserved in frame O prime. And what I mean by that is, in order to show that the Lorentz transformation works, we have to show that this is true. If momentum is conserved in frame O, it is also conserved in frame O prime. So that means that if this is true, then the question that we have to ask is m1 u1 prime plus m2 u2 prime, is that equal to m1 plus m2 uf prime? Oops, sorry, a little messy there. All right. Okay, so let's go ahead and transform. So we have the momentum conservation in O. Let's transform it to O prime. Well, the momentum conservation in O prime is going to be m1 u1 prime plus, oh, I think I already wrote that. I did. I already wrote the one with the prime variables. So let's go ahead and, I guess I'm just rewriting it from the other page. This is a one-dimensional transformation, so we can say u1 prime is equal to u1 minus v over 1 plus v over c squared u1. u2 prime equals u2 minus v over 1 plus v over c squared u2, and uf prime is equal to uf minus v over 1 plus v over c squared uf. And did I get those signs wrong? There we go. It's easy to lose the signs, lose track of the signs. There should be minus signs on the bottom. Okay, so if v is equal to, we have the numbers on the other page. I don't need to rewrite them. We've got v right here. We've got u1, u2, and uf. So let's go ahead and plug in. u1 was 3, v was 1 minus 1 over c squared times 3. I'm not going to bother plugging in c for now. u2 was 0 minus 1 all over 1 minus 1 over c squared times 0, and this is 0. I've gone ahead and plugged in, and so here I get 2 over a number which is less than 1, right? I'm not going to do the number out, 1 minus 3 over c squared. Here I've got minus 1, and here I've got 0. Okay, now let's go ahead and plug those numbers back into our equation. 500 times u1 prime, which is a number bigger than 2, plus 1000 times minus 1 equals 0. Is that true? So you see why I didn't even need to figure out what u1 prime was. Is that true? The answer is no, that cannot possibly be true. Momentum is not conserved in a Lorentz transformation, at least this momentum, P equals mu, is not a conserved quantity. In Lorentz transformation, oh my gosh. So what's wrong? Oh my gosh. So what does Einstein say? Einstein says, oh, well, we already knew Newton was wrong, right? So Einstein says, we have got to figure out a new form of momentum. Oh my goodness, okay, new form of momentum. And so here's the key. We've got a new form of momentum, we've got a new form of kinetic energy, we've got a new form of total energy. We only sort of have a new form of mass. I mean, mass is still the amount of stuff you got, but we've got a relativistic form of mass which is somewhat meaningful, but it doesn't really change the mass of an object. Okay, so the conclusion from Einstein is that in order to make everything work in the correct, Lorentz transformation, we need to come up with a new form of momentum, energy, and mass. Okay, so here's the key. That we're not going to do any derivations here, but it might be pretty obvious. It's not obvious how you derive them, but Einstein comes up with a value for momentum an expression for momentum, which is conserved and does make sense in it is conserved and does make sense in a Lorentz transformation. And it's basically, now you got to be careful here, it's basically just gamma mu. You say, oh, duh, of course. Well, that doesn't come from Lorentz transformation. I mean, and the gamma here, you got to be careful. The gamma here isn't really the same gamma. I mean, it is and it isn't, because gamma before had to do with two reference frames. In this case, the gamma is 1 over the square root of 1 minus u squared over c squared, where u is the magnitude of the velocity of the particle. Gamma in this case is 1 minus u squared over c squared, where u is the velocity of the particle. Oh, relative to any frame. So it's not exactly the same. It's not the same as the gamma where we were talking about changing from frames of reference. So this is our new momentum, and you can check it. You can put this into our conservation momentum here, and you will find that indeed it works. If we were to go ahead and say gamma 1 and gamma 2 and gamma final, then that all works out well. Newton's second law tells us, right? This is the definition of force. It's the rate of change of momentum. So that's what Newton told us. So now force is still that. So Newton's second law, this is Newton's second law. Newton's second law doesn't change, except it is no longer ma. It is d dt of gamma m0u. And you realize I just never told you what m0 is. And there is this is where this is not a constant, right? This is not a constant like it was before. This is the velocity of the particle. So there is something that depends on t in here and something that depends on t in here. So when we take the derivative of this quantity, it is more complicated. And you can read about it in the book that the acceleration is a more complicated function. But this is indeed what Newton's second law now looks like. It's no longer ma. It's only ma in particular situations. Right? Okay. Let me say what m0 is. I didn't say what m0 is. M0 is, so let me go back to the definition of momentum and talk about m0 and m effective. So when we talk about momentum, we say gamma m0u. M0 is called the rest mass. It's the rest mass. What is rest mass? Well, first of all, you can always ask the question, how do we measure mass? What is mass? Mass is the amount of stuff that you have. Actually, there's two different masses, right? Mass is either the amount of stuff you have, or it's a measure of how hard it is to change a body's motion. Remember, that's the inertial mass. There were always two definitions of mass. And inertial mass is, again, a measure of how hard it is to change a body's motion. And stuff mass is the amount of stuff that you have. So this rest mass, in classical physics, those two were the same. Now they're different. This is what gets really cool here, is that we have these two quantities that we couldn't differentiate between. We said, these are both definitions of mass. But now they're different. Because the stuff mass, this may not be obvious, but if you have a baseball and the faster the baseball goes, you don't have more or less stuff. I mean, sure, you say, well, it's bumping into air molecules and absorbing things, especially if it's going close to the speed of light, blah, blah, blah. Well, put the baseball in a vacuum, whatever. It's not losing mass and it's not gaining mass the faster it goes. So the stuff mass doesn't change. The rest mass, which is the same as saying the rest mass, or the mass in the ball's own frame of reference, doesn't change. So the rest mass is the stuff mass, or the mass in the ball's own frame of reference. Whereas the inertial mass is a different quantity. This is the inertial mass. And you can see that the faster it goes, the bigger this is, because remember, as u gets bigger, gamma gets bigger. So that the inertial mass, it gets harder to change a body's motion the faster it goes. That's a really important point in relativity. So this concept of inertial mass, it's an effective mass. The actual stuff in the baseball doesn't change, but it gets harder to move the faster it goes. Not only that, but how much harder does it get? I mean, we can figure this out from the Newton's second law and from momentum, but qualitatively, what happens to gamma as we go faster, right? As you approach c, right, when u, the speed of the baseball, approaches c, therefore gamma approaches infinity, and what happens to gamma m0, which is the effective mass or the inertial mass? It goes to infinity. So it's as if the body has an infinite mass. So one of the things you may have heard about relativity before is that the faster you go, the heavier you get. That's not true. Absolutely not true. The faster you go, the heavier is. But the faster you go, you have this effective mass effect. That you act as if you're more massive. You act as if you get infinitely massive. And so you can't change your mass anymore. But that's due to speed, it's not due to getting more mass. So this quantity, inertial mass, is gamma m0, or effective mass is gamma m0, and that's what increases. It increases because gamma increases. The actual mass of the body doesn't increase because you can always get into the frame of reference of the body, traveling faster and faster and faster. If you're in its frame of reference, then its mass is still m0, the rest mass. Okay, but it's this fact that as u goes to c, that gamma goes to infinity, that the effective mass goes to infinity, that tells us that when u approaches c, if the effective mass gets infinitely large, that means that it doesn't matter how hard we push it, we cannot change its motion. It's Newton's second law. No matter, when you exert a force, you change your body's motion. But if it's got an effective mass of infinity, no matter how hard you push it, you can never change its motion. Hence, a body can't go faster than c. Again, a body can't go faster than c. A massive body can't go faster than c. What about a body without mass? Well, that's a whole different thing. We still, truly believe that that nothing can go faster than photons for other reasons than the speed of light. Now, there are these imaginary particles called tachyons. You've probably heard of them before. And tachyons are these imaginary particles that go faster than the speed of light. They're imaginary because we have never detected them, and because theoretically, according to Einstein's laws of relativity, you cannot detect something going faster than the speed of light. You cannot communicate with something going faster than the speed of light. So it could be that there's a whole... This is really true. This is an aside too, right? It's really true that there could be a whole nother universe where things are going faster than the speed of light. But according to Einstein's relativity, we can't communicate with that universe. This is just freaky, interesting stuff, right? But there's not much point in considering that right now if we can't even communicate or make any measurements in it. In our universe, once you start to approach C with a massive body, you cannot ever get there because your mass gets infinite, effectively infinite, and there's not a big enough force to change your velocity up to C. So you can only approach it. Okay, so that's a little bit about mass, momentum, and force. What about energy?